Have you ever just glanced at a periodic table and wondered about all those numbers? You know, the ones with the crazy decimal points? I'm talking about atomic mass. And you've probably thought, hey, wait a minute, why isn't that just a nice simple whole number? Well, let's dive into that little mystery. We're going to find out why chemistry is so much more than just counting protons and neutrons.
So let's take carbon as our first example. It's got 6 protons and 6 neutrons. Basic math, right? 6 plus 6 equals 12. The mass should be exactly 12. But if you go look it up, it's not. And that tiny little difference is the exact puzzle we're going to solve together today.
So here's our game plan. First, we'll look at the perfect world of atomic weight. Then, we'll introduce a little complication from nature itself. After that, we'll see the clever way science solves it, see how this all connects to building molecules, and finally, we'll understand why this all matters so much. Okay, to get started, we have to build from the ground up. You know, scientists needed a benchmark, a universal ruler they could use to measure all the other atoms. And the atom they chose for that job was carbon-12. This brings us to a really key idea: relative atomic mass. Now, it sounds fancy, but it's actually pretty simple. Imagine scientists put one carbon-12 atom on a scale and just declared, this weighs exactly 12 units. That's it. That's the gold standard. From now on, every other atom is just measured against it. Is it half as heavy? Is it a little bit heavier? It's all just a comparison, a ratio, which is why you never see units like grams next to it.
And you know, in a perfect world, this system would give us these beautiful, clean numbers. Hydrogen would be 1. Carbon, our standard, is 12. Nitrogen, 14. Oxygen, 16. It all just seems so simple and predictable, right?
But as we already know, that's not quite what we see on the real periodic table. Turns out, reality is just a little bit messier.
And here it is, the official number, 12.011. Not 12. So where does that extra .011 come from? I promise you, that's not a typo. It's a clue. And it points to a much deeper truth about how elements actually exist out in nature.
And that clue leads us straight to something called isotopes. You can basically think of them as nature's own little variations on a theme. So what even is an isotope? It's pretty straightforward, really. All atoms of one element have the exact same number of protons. That's what makes it that element in the first place. But they can have a different number of neutrons. So you've got the same element, but with a different weight. They're like siblings, definitely part of the same family, but not identical twins.
Let's look at what this means for carbon. If you could somehow grab a random handful of carbon atoms, you'd find that almost 99% of them are that standard carbon-12 we've been talking about. But a tiny fraction, just over 1%, is actually carbon-13, a slightly heavier version with an extra neutron. Chemically, they act the same, but that extra neutron means they just don't weigh the same.
So, if nature gives us this mix of atoms, what number do we put on the periodic table? We can't just pretend that heavier carbon-13 doesn't exist. Well, this is where science uses a really clever mathematical tool to find the perfect balance.
The solution is called the average atomic mass. And the key word here, the most important word, is weighted. This isn't a simple average. We have to take into account the fact that carbon-12 is way, way more common than carbon-13. So its vote for the final average counts for a lot more. The calculation itself is actually pretty easy. You just take the mass of each isotope, multiply it by how common it is in nature, and then you just add all those pieces together. Let's walk through a real example. Let's use boron. Nature gives us 2 main types: boron-10, which makes up about 20% of all the boron out there, and the heavier boron-11, which makes up the other 80%. Okay, let's do the math. We take the mass of boron-10, which is 10, and multiply it by its 20% abundance, so 0.20. That gives us 2. Then we do the same for boron-11, a mass of 11 times its 80% abundance, or 0.80. That's 8.8. You add them up, 2 plus 8.8, and you get 10.8. Notice how that number is much closer to 11 than to 10? That makes perfect sense, because boron-11 is so much more common. That's the power of a weighted average. Okay, so we figured out the true average mass of a single atom. But why does this really matter? Well, it's because atoms almost never exist by themselves. They love to team up to build everything around us. And those teams are called molecules. A molecule is simply a team of atoms. Anytime you have 2 or more atoms that are stuck together with chemical bonds acting as a single unit, that's a molecule. It's really the next level of organization in the universe. And we can split these teams into two main groups. You've got homoatomic molecules, which are made of only one type of element, like the oxygen we breathe, O2. Then you have heteroatomic molecules, which are made of different types of elements, like good old water, H2O, which combines hydrogen and oxygen. And to understand these little building blocks, we have a simple way to classify them based on how many atoms are on the team. It's a concept called atomicity. A 2-atom team, like fluorine, is diatomic. A 3-atom team, like carbon dioxide, is triatomic. And if it's any bigger, we just call it polyatomic. Knowing this, and knowing the average mass of each individual atom, is exactly how scientists can predict the mass of an entire molecule. So, we've solved the mystery of the decimal points. But why did we go to all this trouble? Why does this average number matter so much in the grand scheme of things? This quote really gets to the heart of it. Those numbers you see on the periodic table aren't for some imaginary, perfect atom. They represent the reality of that element as it actually exists in nature, a mix of all its isotopes. It's the most honest and the most useful number for doing any kind of real-world calculation.
So let's just quickly recap what we've uncovered. We started with a standard, carbon-12. Then we discovered that nature complicates things with isotopes. We learned how science solves this using a weighted average. And we saw that this super accurate average mass is the absolute foundation for all of chemistry, letting us build and understand molecules. And this leaves us with one final, fascinating thought. The atomic masses we use are really a snapshot of our planet, right now. But what if that mix of isotopes slowly changes over millions or billions of years? Could the fundamental constants of chemistry actually evolve over time? Now that is something to think about.